Good afternoon, and thank you for attending this panel discussion on operational detection capabilities at the CTBTO. Since 1996, a major international effort has led to the establishment of the monitoring regime for the CTBT. The International Monitoring System, the IMS, is a global network that uses state-of-the-art seismic, hydroacoustic, infrasound, and radionuclide facilities to monitor the Earth, oceans, and atmosphere 24 hours a day, 7 days a week, for signs of nuclear explosions. The IMS data, which is then sent to the IDC, as we learned the other day, this is gigabytes a day, is then analyzed automatically by specially designed computer programs and then by experts to identify events that further require attention and analysis. During the last 29 years, this system has detected signals from each of the 6 nuclear explosions by the DPRK, the Fukushima accident, the Beirut explosion, and the Hunga-Tonga-Hunga-Haipai volcanic eruption, as well as many other natural and man-made events. The data recorded by the system are widely considered to be unique and a treasure trove of knowledge with a broad range of civil and scientific applications. Today, the CTBTO data are not only being used to detect nuclear explosions, but also to investigate the impact of climate change, warn about tsunamis, or to track radiation on a global scale. During this panel, we will explore how the detection capability of this system has evolved through time. In particular, we will discuss the development of station technology, the IMS network, the IDC processing algorithms, and the benefits of considering monitoring technologies in an integrated way, before finally thinking about the future developments how the future developments could further affect the detection capability. But before we talk about these questions, I want to introduce the panel. So on my far right is Alice Camigeau from CEA. Alice, could you say a few words to the audience and introduce your work?
Yes, so glad to be here. Just to introduce myself quickly, after the obtainment of a master's degree in computer science with a specialization in AI, I'm now a PhD student at the French NDC, and I'm working with the different collaborators, European collaborators you can see on this slide, on the development of deep learning algorithms, such as neural networks, to the near real-time modeling of infrasound transmission losses in the middle atmosphere. And the objective of our work is to develop operational tools to meet the near real-time requirements of the CTBT and of the French NDC. And this work can represent the first step toward the assessment of the global detection capability of the infrasound network of the IMS, and so that's why I'm here today. Thank you.
Thank you, Alice. Next to Alice, we have David Delasto from the University of Washington. David, could you please introduce yourself and some of your work?
Hello, yes, I'm David Delasto from the University of Washington, and I actually work at the Applied Physics Laboratory, which is a U.S. Department of Defense affiliated research institute. There's about 5 of these across the United States that help understand important things facing global security. And my lab's actually worked a bit with CTBTO to help do environmental modeling for deployment of the hydroacoustic station on Crozet, and has actually done some of the development of how we can keep these systems moving into the future by retrofitting and cutting cables on the bottom, and so we can replace parts dynamically. I've been working in underwater propagation since I got my PhD almost 20 years ago, and have found that this data set is rich because we have high bandwidth over the entire globe for over 20 years of the IMS and even data from before. So I'll give some examples as we hit some questions.
Thank you, David. Next to David, we have Yuichi Chikijima from the Japan Atomic Energy Agency. Yuichi, could you just introduce yourself?
Thank you. Good afternoon, everyone. My name is Yuichi Kijima from Japan. Since 2010, I have worked at the Japan Atomic Energy Agency, JAEA, as a radionuclide data analysis and radionuclide laboratory staff and radionuclide station operator. And then, from 2021 to 2024, I had worked at IDC as a radionuclide expert, and then I came back to Japan, JAA. That's it, thank you.
Thank you very much, Yuichi. And finally, next to me is Saeed Mikhaima from the Egyptian National Research Institute of Astronomy and Geophysics. Saeed, could you say a few words about yourself?
Hello, good afternoon. My name is Saeed Mikhaima. I work in atmospheric transport modeling field. That's all, and I am member of National Data Center in Egypt.
Thank you very much, Saeed. And finally, my name's Stuart Nipras. I work for AWE Black Nest, which is the UK NDC. I'm a seismologist. I do a lot of waveform simulations. But for the last few years, a few of you would have seen me at Working Group B, where I've been analyzing some of the new IDC processing algorithms to implement into provisional operations to hopefully help the analysts in the future. OK, so you met the panel. So let's start with our questions. So the first question we're going to talk about is, how has the IMS detection capability evolved over time? And for this, we're going to start in the ocean. So David, if you could please have a go at answering that.
Yeah, so the initial concept of being able to detect a nuclear explosion underwater was first examined during the prototype International Data Center period, which was from roughly 1996 to the early 2000s, which gave birth to the IMS and the IDC. And during this time, we had hydrophones that were actually part of a larger network operated by the US Navy, and they were able to stream this data via telemetry to see if we can actually localize sounds in a continuous sense, not just when people were listening. One of the discoveries we made during that time was the prevalence of earthquake noises, hydroacoustic noises coming from across the globe. And part of the informative part we got from having this prototype era was that trying to associate events that are maybe happening simultaneously in different locations, that it would be helpful to have multiple hydrophones. And that informed the triad of hydrophones that we now have either on the north or south end of an island or off the shore, such as the one in Australia. I would say that the evolution from single hydrophone to triplet hydrophone was the major change probably that happened during the PIDC to the actual installation, and probably informed the treaty specifics. Moving forward to how have we evolved since the establishment of the IMS stations, they haven't changed in terms of their design since the first ones went in. But we do have a lot more knowledge of the ocean environment. We now have satellite measurements and a very active ocean profiler measurement system called the Argo system, where there are over 2,000 floats sampling the deep ocean temperature. So we can see what the stability of the ocean temperatures are instead of just treating these as static values from ocean atlases. Actually, we'll present a poster tomorrow. I have a slide here showing the, I guess, the Wake Island station here, where I've had a lot of focus. And on the, I guess that would be maybe your left side there, you can see the two stations that were established for the PIDC era in the yellow circles, and then the current stations that are now at Wake Island, H11 North and South. They're actually pretty close, and you can see that transmissions that we have been doing to measure ocean temperature from Hawaii that travel over 3,200 kilometers are received on these stations. The ones that were received in the 90s actually look very similar to the ones that we received now in the modern era. On the bottom right there, you could see the Argo temperature profile there, which has been operating for 25 years, and the modern measurements of this acoustic transmission, and seeing that there's a shift in the travel time over this path that's consistently tracking the deep ocean temperature that we're measuring. So thinking about what we can do even moving forward with IMS measurements, we can take ambient noise measurements, things that aren't necessarily from explosions, and we can actually infer what the ocean temperature is, both to inform climate models and also to provide a better localization technique on the IMS network.
Thank you very much. So we're going to move from the oceans now to the land, and I'm going to talk a little bit about seismology. So I've just plotted up here images from the threshold monitoring tool that you can actually access via the secure web portal. And I've got 4 plots, 3 of them for the 29th of July. The top left is in 2005, the top right is for 2010, and the bottom left is the 29th of July 2025. And these estimates the smallest or average hypothetical seismic event that could possibly be detected by at least 3 primary IMS stations. And it takes into account things like noise variability, interference signals, coda from large earthquakes, gaps in the data, communication, or processing. So if we were to take the top left plot to begin with, and we were just interested in a particular place on the globe, what would be the sort of smallest magnitude event that we could detect? If we were to take southern Australia, let's say Adelaide, in 2025, this value would be about 4.25. When the station coverage increased through the next 5 years, and we look at Adelaide in 2010, this decreased to about 3.8. And then if we fast forward again 15 years to the 29th of July 2025, this value reduced to about 3.3. So in the space of 20 years, we've nearly got an order of magnitude lower. But the plot to the right-hand side is for 3 hours later. And why is there such a difference? You can see on the bottom left-hand plot that the colors are generally greens and yellows, and these are quite low magnitudes. These are like 3s, 3.5s. And then 3 hours later, suddenly it all turns blue and magenta. And so now, in Adelaide, the lowest magnitude event we would likely detect by the IMS is a magnitude 4. So what's happened between these 2 images? And it's quite simply that there was a large magnitude 8.8 earthquake in Kamchatka. And in the preceding 2 or 3 hours, there was tens to hundreds of aftershocks. This flooded the IMS with seismic data, so it's really, really difficult to pick up the smaller magnitude events. And so threshold monitoring, or detectability, if you like, depends on a large number of things. It's not just putting more stations in the ground. You have to think about noise levels, you need to think about data, communication and processing, and then interference signals. So it is a living, breathing animal, if you want. So that's enough from me about seismics. Alice, could you say something about how the infrasound network has changed?
Yes, sure. I can say that during the first preparatory commission of the CTBTO at the end of the last century, it was said that 60 IMS infrasound stations would be sufficient to ensure 1 KT detection capabilities by at least 2 stations at any point of the globe at any moment. And this number of 60 stations was found using and doing simulations using climatological models to represent the atmospheric dynamics and yield scaling empirical relationships. And since the end of the last century, we have made a lot of progresses for the atmospheric dynamic descriptions. So, for example, we can use now meteorological products. We can use a model with finer time and space resolutions. And we also have made lots of progresses in modeling, propagation modeling. We can use AI tools, and also in the description of the background noise level at each station, which is very important to assess the detectability. And with all of these progresses, we have remade simulations, and we confirmed this number of 60 stations to ensure the goal of the CTBTO. And now the IMS network, infrasound network, is complete at approximately 90%, with 54 infrasound stations up to 60. And here you have an example of all the certified IMS stations, infrasound stations, even if one is missing because it was certified just 2 weeks ago in South China. But you can still see the distribution of these stations, as well as the strong time and space variability of the detection thresholds. So you can see, for example, the strong time variability between 2021 and 2025, and you can see seasonal variation in the detectability. And this is mostly due to the strong variability of the atmospheric medium and of the wind. And you have also strong variability in the background noise level, which are two challenges for the infrasound detectability. So.
Thank you very much, Alice. So we're now going to move on to radionuclides. So Saeed, could you talk a little bit about the radionuclide network?
So, in radionuclide network, it's important to detect any nuclear test of magnitude of exclusion of over 1 kTNT equivalent. 1 kiloton of TNT equivalent. So designing radionuclide network, it's important to consider that moving from the source to station, we should consider the distance between the stations. The station should be in the downstream of the wind. Also, the distance should be short enough to make because the release diluted with time. So to get a minimum, to get a concentration above the minimum detectable concentration, the station should be near enough or a distance enough to get concentration above the minimum detectable concentration. So the design. So the design of radionuclide network, as seen in this graph, we have blue dots represent particulate station and red dots represent the noble gas. The distance, intermediate distance between, in average, between particulate station is about 1,600 kilometers, while the distance between noble gas station about 2,300 kilometers. So to measure the detectability of this radionuclide network, we should make some assumption regarding the source strengths and regarding the minimum detectable concentration. In this diagram, this is represent network coverage for Xenon 133, assuming one minimum detectable concentration of 1 megabecquerel per meter cube. Using 37 noble gas stations. As you can see, the average of global average of network coverage is about 42%. But actually, this smaller value, due to there is the tropical region we have not covered. And we will discuss in some detail why this is a problem in tropical region. But if you look for particulate station detectability, you can find in this next slide. You can find it's better. We have now network coverage about 65%, and also the same. There is a tropical region. We have some region without coverage. And we can see that the yellow colors covered a large area, which is about 100% of times. There is at least one radionuclide station detected the event or release. So the reason for this small detectability in the tropic, in the next slide, okay. So it's important to show the shift from the previous one. And this is different in the December 24. We have first from 1 to 6 December. This is network coverage. For the last 10 days in December, we have another detectability. So the detectability of the network changed with time due to atmospheric motions. So it's variable of time due to atmospheric dynamics. And also we can measure the detectability using what's called threshold monitoring. And this is available, both network coverage and threshold monitoring available in IDC, in WebGrep and NDC in a box. The reason for, okay, there is a missing two slide, but I can talk about the reason for for small detectability in the tropic. Actually, we have two weather regimes, one in northern hemisphere and other in southern hemisphere. Both two regimes are mainly westerlies. The wind moves from west to east. While in the tropic, we have easterlies from east to west. And the difference in magnitude in wind speed that we have high wind speeds in mid-latitudes comparative to the tropics. Is the difference sometimes in order of tens, while we can get a magnitude of wind speed about 1 to 1 meter per second or 2 meters per second, while in some time we get tens of reaches according to the vertical level, because when we're talking about release from source, we talk about dispersion in 3 dimensions, not on surface. But so in sometimes we have westerly jets in reach about 50 meters per second in mid-latitude. So the tropical region actually make a barrier between two regimes. So we have two regimes decoupled by barrier westerlies from the east to west. And this barrier is slow, and as we said in the first slide, it's important to detect it is the release move from the source to station. But if you have a slow motion, wind speed, slow motion, it is a release decade before it reaches the station, and the concentration will be blue, minimum detectable concentration. So the current situation, we have a good network coverage for most of the globe. Radionuclide design is good, and the gap in tropics is not related to the network. It is related to atmospheric motion dynamics, and this is not easy to solve actually by increasing station. Increasing station not well solved. If it will be needed a condensed network, and it is well cost. But because actually the weather in tropic is convective motion rather than moving in zonal or that's all regarding the radio network coverage and detectability in radionuclide. Thank you.
Thank you very much, Saeed. So I think you, myself, and Alice have all shown that detectability changes with season and times depending on what's happening in the world. So we've talked a little bit now about the network, but what about changes in stations and how that might change the detectability? So Yuichi, could you talk a little bit about the improvements in the noble gas stations? Thank you.
Thank you. Regarding noble gas, I think noble gas equipment has greatly improved. For example, Sauna 3 and Sparax NG that are new version, new generation of the equipment have been developed. They have shorter correction time. That is, they have much better time resolution, and also they have lower MDC, minimum detectable concentration. That is, they can detect smaller radio xenon. So I think to continue to develop new, better noble gas equipment is very important for detection capabilities. That's it. Thank you.
Thank you very much. So I think in the first questions we talked about increasing station density helped, changing the technology of the stations have helped. But as I said in my introduction, detectability isn't just about stations, it's also to do with what you do at the IDC, your processing algorithms. So are there improvements in the IDC algorithms that we could have to increase the detection capability, and what could be the impact of AI? We've heard a lot about AI yesterday in the Quantum Day, and I wonder whether we could touch on that. Alice, could you talk a little bit about infrasound?
Yes, sure. So, for example, we can imagine improvement in the algorithm for waveform parameter estimations, so the apparent velocity and the azimuth. And so at the IDC currently we use the PMCC algorithm, but it was developed at the French NDC, so the CA, the MCML algorithm, which allow, for example, to lower the SNR to -5 decibel, and which would allow in the future to do multi-source separation. So meaning the characterization of the waveform parameters for interfering signal arriving in the same time frequency cell. And the MCML algorithm can also provide a better estimation of the uncertainties related to the parameters, so the apparent velocity and the azimuth. And this would help to provide better uncertainties using, for example, algorithm for source location. And to talk about AI, several studies try to employ AI models to do signal identification. So, for example, to identify signal of interest in a record, or to do source classification, infrasound source classification. And more in general, AI models can be used to produce operational tools and to meet, for example, the near real-time requirements of the IMS or of the CTBTO, or to process a large amount of data. So, for example, I don't know, all the records of the IMS stations since 20 years or stuff like that. Yeah.
Thank you very much, Alice. David, Alice mentioned PMCC. Is this something that can also be used in the hydroacoustic world? And does that help?
Right, and maybe there's a slide here just to show an example of the PMCC applied to hydroacoustics. So this would be available to the NDCs as an automated tool to detect the speed at which the waves of a detection are coming across the array. But it also gives you the direction. One of the things that could be quite useful in having directional information from an explosion or an impulsive source is that as its sound is traveling through the ocean, it can reflect and refract off of islands and off of shorelines. An example of this would be the San Juan submarine that imploded in 2017. And PMCC was deployed here. You can see on the upper right there the detection of multiple arrivals here coming up to 30 minutes apart from each other as the sound is traveling across the ocean. One of the tools that we can use with having multiple arrivals is that we can actually proliferate the number of stations we have. This sound was detected on 2 hydroacoustic stations, but having all the refraction pieces coming in from the shoreline, it almost sets up a virtual station, so you can actually backtrack the azimuth to the actual source if you're able to make that association. And I think that's maybe one of the lead-ins to possibly using AI to help kind of have a pre-brain for the reviewed event bulletins and to help the analysts take off a load, is that an association of different sounds that may look very different as they're going through these propagation paths could be done by a tool that's being trained on historical data. We have 20 years of very well cataloged data that we can determine, is this an earthquake, is this an explosion, is this an implosion, or is this some biological noise that could really help take a load off of what it becomes a very timely and exhaustive effect by the analysts here at CTBTO.
So just a follow-up question. You said you have 20 years of data. Is that readily available to be used to be trained in AI?
I mean, I would imagine so, just the 20 years of the IMS data and how far back the REBs go to have the data being labeled. I would think that using these event timings and the locations, one can take the simple propagation models and pull these signals out. I believe all of these signals are going to have a pretty high level of amplitude relative to the noise, so it would be quality data for doing this association. I think similar to your point earlier about when the Kamchatka earthquake was happening, that we have a reduced threshold, things like PMCC, which perhaps could be another piece of data that is input into an AI model to help identify, is this signal part of the signal of interest or not, all could be kind of recategorized, because PMCC has not been applied to hydroacoustic for 20 years, but that data is still there in that capacity.
Okay, thank you very much. So in terms of seismology, we saw lots and lots of posters today actually on looking at deep neural networks to help identify seismic arrivals and to identify phase peaks and the seismic arrivals. And these have been used not only in the nuclear monitoring community, but also in the wider academic community. And they've been shown to work really quite well in the local to regional environment. I guess the position we're at now is whether these can be retrained and used globally in terms of a nuclear monitoring community. So there's algorithms out there like PhaseNet and EQ Transformer. There's also quite a lot of work at the moment on denoisers. These denoising algorithms decompose, again using deep neural networks, decompose the signals between noise and seismic signal that you're interested in a completely different way that you do when you just do normal bandpass filtering. But again, we need to understand what these algorithms are doing to the actual waveforms, particularly amplitude, before we can use them for other things. So there's lots of work in this field. I guess we just need to see how it's going to progress in the coming years. I mentioned earlier, and it's been mentioned a few times already this meeting, about there's net visa. So once you have all of these detections, you need to form events. So at the moment, the IDC has something called Global Association, but NetVisa has been developed over the last 15 years. It's a Bayesian method to find the best set of events given a list of detections. And it's been shown in multiple presentations at the Waveform Expert Group and in academic papers that actually NetVisa does a better job. You get more events, the events are better. So all of these things are there to help the analysts when they are analyzing the events. There's other things out there, like the generalized F detector, which is a statistical method for detecting coherent signals on recorded arrays. So there's lots of interesting work going out there, particularly in the AI field. I guess we just need to understand what data is being used to train on and whether that's applicable to the world we work in. So, Yuichi, can you say a little bit about noble gases and how algorithms could help?
Thank you. I think noble gas, especially radioxenon, is very important nuclides for monitoring nuclear tests. But nuclear facilities such as nuclear power plants and medical isotope production facilities also release radioxenon into the atmosphere. So it is not easy to say that the radioxenon detected at radionuclide station is originated from nuclear test or nuclear facilities. So I think radioxenon background estimation is very important for improving detection capabilities. That's it. Thank you.
Okay, thank you very much. Saeed, I'm going to turn to you now. So do you have any thoughts about how AI could be used and any downsides to AI, perhaps, going forward?
Okay.
Sorry, big question.
Actually, we are at the beginning of revolution, AI revolution. And this revolution will will reduce the work overload, and all of us use AI, and it's helpful for many tasks. But I am, in some regard, I can consider myself an old man. I should have cautions about using AI. Actually, the long-term impact we don't know until now, but it's important to use AI, but not make AI lead us. Actually, as I understand, the AI work like this: we training model using historical data. We search the model, search for pattern, some correlations. And based on these correlations, they make a model, the model based on historical data. So, for example, in weather, for example, Google made a weather forecast using ECWF data. And the paper explained by Google teams, they said that they now made a model that overperforms the ECWF by in 90% or more than 90% of the cases. So they used data by ECWF, and they now have a model outperformance than ECWF in 90% of data. But what about the 10%? What if this 10% is with extreme weather event? It will be catastrophic in some cases if you rely on AI without cushions. So, because actually AI in this regard looks like black box. Not for the user, but also for the developers of the AI. It's black box. The machine learns by itself, and there is no control which pattern is included and which pattern is not included. Okay, there is some technique to make what's called physical-based AI. The developers make a constraint in how that model developed, and they enforced the model to look like a physical model or a mathematical model we built. So all of us should use, or we should use AI, but with cushions. That's my thought.
So buyer beware is what you're saying. Yeah. So I think for the first two questions, we've talked a little bit about the station network, the technology, and the algorithms that could be improved. But we've sort of talked in vignettes where we talked about each individual technology separately. So how can detection capability improve by jointly considering monitoring technologies, and what has to be done to achieve this? Sylvia, in her talk, showed an example where she used the waveform source location and origin time to set off her ATM models. But is this something, data fusion, something that's easy to do, and what do we need to do to be able to do this properly? So Saeed, I turn to you first.
So the data fusion in our CTBTO community means that all data from all technology should be combined together to estimate the source. So in that regard, the Bayesian approach gives us the logical framework that can be used to combine different technology, the solution by different technology, in a logical framework. For example, if you look for the first equation, this is this famous one by Bayes theory. Statistical law. This is known more than it's known from 1850, but it's currently heavy used by scientists. In this regard, it depends on the technology. For example, in radionuclide technology, if I use only radionuclide to determine the source, my focus will be determines what's called likelihood function. The likelihood function in this regard can be estimated by using second equation. We calculate the difference between the observed concentration and modeled one by using atmospheric transport modeling. And the difference, we try to minimize this difference, and the difference between them will be considered as an error, and we make a likelihood function as a Gaussian of this cost function. So it's looked like a Gaussian distribution of the error. So likelihood function in this regard, we consider the observed concentration and the model concentration, and also the uncertainty in the observation, sigma ops, and the uncertainty in the model. So these equations combine all what we know regarding the atmospheric model, regarding observed concentration and uncertainty in both. So we have now this likelihood function. But also we can combine the solution from seismic, from infrasound, from hydroacoustic, using what's called superior probability density function. So in this regard, in Bayesian framework, all information are transformed from to what's called probability density, and this is represent what we know and how our confidence about this information. So using this equation multi-time, we can call Bayesian update. By having new data, you have more confidence about the source, and so this equation represents the logical frameworks that we work to make a data fusion from different technology to get solution according to all available information and uncertainty in this information.
Okay, thank you very much. Yuichi, what about using HPC and machine learning? Could that help us?
Thank you. Can you show? So this slide shows about the example of calculation formula of Bayesian approach and uncertainty. The left calculation formula are based on conventional statistical approach and not taking into account uncertainty. On the other hand, the right calculation formula are based on Bayesian statistical approach and taking into account uncertainty. So as you can see, calculation formula becomes basically much more complex when we use Bayesian approach and or take account into uncertainty. So I think machine learning and HPC, high performance computing, can help and support these complex calculations. That's it from my side. Thank you.
Thank you very much. So Saeed and Yuichi has sort of laid down perhaps mathematical frameworks, machine learning, HPC, on how data fusion can actually be done. But as I said in the introduction, we now have 29 years of IMS data. So do we actually have examples where we've had events of interest, where we've pulled together different technologies, and that's helped us to understand that event in more detail? Alice, what can you give us on that?
Yes, sure. So certain subsurface events, so some earthquakes, some explosions, or for example the strong volcanic eruption of the Unga Tonga in 2022 can generate seismoacoustic waves which can couple at the different interfaces, so for example between the ground or the atmosphere. And for that case, the combined use of, for example, seismic phase points and corrected azimuths can really help, for example, for the source localization of the event. And in general, I would say that the different processing algorithms, so for example, PMCC or AI models, as we already discussed, and also our expertise about them can really be shared across all the technologies to improve localization and also the characterizations of the parameters. So, yeah.
Okay, thank you very much. David, is there any examples in the seismic hydroacoustic data fusion that has shown potentially the use of combining the two different observations?
Well, most definitely, in one of the distinctions, maybe, if you're not familiar with what are called hydroacoustic stations, there are hydrophones, which are about 1 mile down below the surface of the sea, that are detecting acoustic waves. But there are also stations called T-phase stations, which are on remote islands, which are going to detect acoustic waves that are traveling through the water, getting coupled back into the land, and traveling as a seismic wave, but at a much higher frequency than perhaps a typical earthquake seismometer would be recording. There are some examples that are quite important. There are very few hydrophone stations actually in the network, a limit placed on it, and it cannot be expanded based on the line of the treaty. For example, in the Atlantic, there's one station with hydrophones, this Ch1 here in the figure that we showed with the San Juan. And so when that event happened, we were able to actually look at seismic stations on the continent of South America and locate the event that happened when the implosion happened offshore. And that actually provides another data point, a timing event that we can localize and reduce our residuals in trying to find out where a source is. So seismic and hydroacoustics are very much connected to each other, and any really large event, such as a nuclear explosion, will be detected on both networks, and they can be used, especially with the hydroacoustics, to really pinpoint the location to meet the mark of the treaty.
Thank you. You mentioned T phases. So T phases are interesting phases. Do we really understand how and where T phases are generated? So by using them, does that help improve locations and our understanding, or does that add additional error to what we might be doing with just a plain ordinary seismic phase and hydroacoustic H phase?
I would say that, and perhaps leading to maybe some of the limitations we have in the IMS network, but the fact that now in the modern time we have a lot more ocean acoustic observatories out there that are recording sounds on the coasts of North America and off of Japan, and using a new technology, including like the distributed acoustic sensing DAS systems, which are these long arrays. We can actually with high accuracy, find out where these T phases come from. And like you said, the generation of T phase, the ground is shaking, and if we have a flat bottom ocean, there's no mechanism to actually radiate that sound into the water. It usually comes from some topography. We're finding that there does appear that a lot of the T phases are actually generated at the bottom of ocean trenches, and they may be different from the location of where the epicenter of an event was. Now, for a test nuclear explosion or an explosion in the water, those will come from the same place. And we do see, just looking at seismic sources, the example, or explosion detected on seismometers, the example being the San Juan. Because those stations are land-based, you have a bias of where that location will be. So I think in terms of identifying physics of an earthquake may be more complicated, but for explosions, they definitely are synergistic.
Thank you very much. So we've come on to our final question for the panel. We sort of talked a little bit about the past and the current state of the systems available to the CTBTO, but what about the future? Are there improvements in both technology and algorithms that could increase the detection capability? So I'm going to turn to you first, Yuichi.
Thank you. Since noble gas equipment is very sensitive device, it sometimes or often malfunctioned. That is, it has troubles. So the data availability is not often 100%. And even if the data is generated, the quality of some data are not good because of troubles of the equipment. So I think to strengthen maintenance is very important. This is my first point. And the second, I think to develop new categorization is very important in the future. The current categorization of noble gas have 3 levels: level A, level B, and level C. Level A means no detection of radioxenon. Level B means radioxenon was detected, but its concentration is within normal level. That is low level, low concentration. And level C means radioxenon was detected and its concentration is abnormal level. That is high level. But because of background, it is possible that level C detection is originated not from nuclear test, but from nuclear facilities such as nuclear power plants. On the other hand, it is possible that level B detection is originated not from nuclear facilities, but from nuclear tests. So I think to develop new categorization, taking account into background is important. That's all from my side. Thank you.
Thank you very much. Alice, do you have any thoughts about infrasound, where this could go in the future and which could help detection capability?
Yes, so I think one of the most important challenge to improve the detection capabilities of the infrasound network is the reduction of the background noise level, at each station. And to do so, several techniques can be developed, like passive noise reduction techniques. For example, the reset type system, which has been optimized in recent years to be more robust against environmental issues, but also to account for the instrumental response, both in phase and amplitudes. And in general, all the infrasound stations of the IMS network are not equal regarding the background noise. For example, you can have some stations next to noisy areas, so wind noise or microbaromes, so the infrasound generated by the ocean waves, for example. And so it's really important to characterize well this background noise. And also, I can say that to reduce the uncertainties regarding the parameter estimations, so as I said earlier about the apparent velocity and the azimuth, it can be interesting to optimize the design of the AMS stations, and so the number of sensors, but also their locations within a station. So, and finally, maybe use AI models to meet some requirements, such as near real-time modeling, which can be complicated with classical algorithms. So, yeah, I would say that.
Thank you very much. That's both of you that have mentioned background noise now. It's something we need to definitely think about in the seismic world as the globe is getting ever more populated. The people are encroaching closer and closer to our stations, and with things like renewable energy, wind farms and wind turbines, they can cause noise on seismic stations. So it's something we definitely have to think about going forward. Saeed, how would you like to progress our detection capability with the CTBT?
So actually, during 29 years of radionuclide network, we have the CTBTO community works well with this data, and now we get lower minimum detectable concentration. And if you compare the detectability 20 years ago and now, we have a higher detectability. But I'd like to actually to mention something regarding uncertainty in the data, because uncertainty for ordinary people and sometimes for some decision maker is bad thing. They don't need to hear about uncertainty. They need sharp and solid conclusion. But in science, we always work with the data, and we know every instrument has its tolerance error. Every mathematical model has its approximations. So it's important, and it's very important to consider this uncertainty, and also to be clear about the hidden assumption in our treatment, in our analysis. Because sometimes we use some assumption and we don't know that we use it. So one of advantage of Bayesian framework, that converting the information, the models, and also the assumption to mathematical formula. So now we have a clear that, so this framework what's called force us to be clear about hidden assumption, about the uncertainty in the data, about approximation in the modeling. So I recommend to think in this framework, and that's all. Thank you.
So we need to think about our errors and being able to describe those errors properly to people and what they actually mean. Thank you very much. David, I know you mentioned in your last one things about DAS. Do you have anything else to add? We are very short on time.
Right. I think just in terms of the hydroacoustic stations had all been installed, and we're now entering into this very expensive maintenance phase as things maybe fall apart. And I believe that implementing things like DAS, where we can use infrastructure that's already there but damaged to basically do the same thing we were doing before, is a possibility. And I do believe that will require at least operationally, some type of reassessment of the treaty and agreements. But I believe that using that in auxiliary stations from other countries, that we can actually find events that are very important, and we can learn a lot from them and improve the mission of actually knowing where these events happen, if they ever do.
Thank you very much. So we are going to have to finish the panel now. There's been a slight change to the schedule. But before I go, I'd just like to thank all the panelists, and I hope you enjoyed our discussion today. Thank you.